Today we are integrating with respect to y. All right, so as you guys know, we did this stuff a little while ago. We want to find the area under the curve. Now let's just estimate it like using the Riemann sums. Okay, real quick, just for the heck of it. So I'm going to do a left-handed Riemann sum. You don't need to copy this slide. I'll stop there. I'm not going to go to the 7. All right, so there's that, right? So the base of my rectangles are all, what? 1 here, right? We call that delta x. You guys remember delta x? It's where you subtract the first from the last and you divide by how many rectangles there are. So that would be 6 minus 0. There's 6 rectangles, so each delta x is going to be 1. And those represent the bases of each one of your rectangles, right? And how do you find the heights of the rectangles? It's the y values, right? It's your y values. So you're going to have y1 times delta x plus y2 times delta x. And when I say y2, what I mean is like this is y1, this is y2. Those are the heights of your rectangles. So base times height, and so on, all the way up until we get to the 6th rectangle, and we have that. And that's an estimation of the area. Now, if I want to find the exact area, what do? It's an integration, right? And we're going from what to what? 0 to 6. And my function that I would be integrating is what? Plus 3, right? And we're integrating with respect to? And that's what it would look like. And it would give us a certain answer, which, since this is actually a triangle, we can find the exact area just using geometry. It looks like the base is 6 and the height is 3, so that's 18 divided in half is 9. Okay, so that's just review. We talked about a Riemann sum there and how it approximates an actual integral, what delta x is and what the heights of the rectangles are, just the y values, right? So what we're going to do now in the next slide is we're going to look at this from a different perspective now. I'm gonna rewrite this equation. It's not going to actually change the equation. It's just going to change the way it looks. Okay, so I'm going to get x by itself instead of y. So like I'm going to minus 3 over here to the other side first. Then I'm going to multiply both sides by a -2. And I've got that. It's still the same line. Okay, so but the difference is that now I've got my y as the input and my x as the output. So I can plug in any y value and it'll give me the x value that goes with it. So for instance, what's the y value of this point right here? 2. So I'm going to plug in 2, and what should I get? You should get 2. Let's see if it works. It does. So it's the same equation. It's just that it makes the y an input instead of the x. You still get all the same points, so it doesn't change the line. But what we have now is we have, instead of, like on the last slide, we had this equation. This is a function of x, which means that x is the input. But if I get the x by itself instead, what was it? Plus 6? Yeah, it was plus 6. If I get the x by itself, this is now a function of y. It's the same equation, really. It's just written as a function of y instead of a function of x. That makes sense? Okay, now what's the significance of that? Well, I'm going to be integrating this to find the area under the curve. But I'm going to be, since my input variable is now a y, I'm no longer integrating with respect to x, but now I'm going to be integrating with respect to y, right? And the function I'm integrating now is this. What are my limits? 0 to 3 now. You guys see why? No pun intended. You see why? Because now, instead of integrating from left to right, we're integrating from bottom to top. Okay? And that's what we call integrating with respect to y. Now, I brought in the whole Riemann sum rectangle estimation thing. We're not going to do anything with that with these, but I think it's relevant because, you know how I said we're integrating from bottom to top instead of from left to right? So what that would do is instead of having vertical rectangles, we're going to end up having horizontal rectangles. Okay? Instead of delta x, we have delta what now? We have delta y's as the little bases of each of these. And each of these lengths are what kind of values? Those are x values. That's x1. Here's x2. They would give you the same answer because you're finding the same area, right? It's just that you're doing it differently. Instead of vertically, you're doing it horizontally. Okay? So that's what integrating with respect to y looks like. It's where you have a function where the input variable is a y, and your limits are y values, and you're thinking of it as integrating from bottom to top instead of left to right. Okay. Now, I don't know if there's anything else on that. There it is. Just a summary of what we just talked about. This is what we're used to. Integration with respect to x gives you vertical rectangles if you're doing Riemann sums. Integration with respect to y gives you horizontal rectangles. So why do we want to do that? Let's start with something simple first. This one's a little bit more complicated. Let's look at this one. Why would we want to integrate with respect to y? Well, usually when we integrate with respect to x, we're always trying to find the area between the curve and the x-axis, right? But couldn't it also be an equally valid question to try to find the area between a curve and the y-axis, right? And so in that case, it would be better to think of this as a function of y, and you're integrating from here to here upwards with these horizontal rectangles, so to speak. So that's one reason why. Okay. Another reason why was actually something that maybe numbers 51 and 52 could kind of like give you a slight grasp of from your homework last night. You know, on those problems, you had to break it up into separate integrals, right? All right. Well, let's take a look at this problem here. So right now, if I think of these two functions as f of x and g of x, if I wanted to find this area here, I would have to break this up into two parts. Where would I break it up at? Right there. If I'm looking for just this area right here, that's an integral from where to where? 0 to a, and that's the area under which function? Just under the f, right? But over here, if I want this area, that's an integral from what to what? A to c, and that's the area under which function? G. So you could find the area that way. That would work. Just breaking it up into two pieces. At that point where they cross, it just switches functions, right? So you just have to do two separate integrals. However, over here, if you think of this as a function of y and a function of g, this one gets a little bit complicated. I should have said something before I came to this slide. So you guys, before I talk about this one, you guys remember how like when you're finding area above is positive, area below is negative? Or in another way of speaking, when you're finding area between two curves, the one that's higher up comes first, right? And the one that's lower comes second when you subtract them. All right, now when we're going horizontally instead of vertically, right? If I'm going this way, then which one of these functions I'm trying to find this area now, right? You guys agree? So don't you guys agree that's an area between two functions? It is, right? But they're functions of y because we're going horizontally now. Which one would come first? Y. There you go. So if you look at it horizontally, G is greater. Why? Because it's further to the right. Anything to the right is greater when you're going horizontally than something to the left, right? Okay. So it would be G minus F, and that would be from what to what? Be careful here. And because we're integrating with, since I'm going horizontally, we're integrating with respect to y now, right? I would be going from what to what? 0 to k, right? We're going vertically from here to here. Okay, so what's another reason why we might want to integrate with respect to y then? Well, it may be easier, less work. So instead of setting up two separate integrals, you could actually just create one integral instead. Okay, so that's another reason. There's two reasons why. One is sometimes it just makes it easier to find the area under the curve. And other reason, maybe they don't want you to find it to the x-axis, they want you to find it to the y-axis. So that's why we care about that. But honestly, as far as what we're doing, very little is going to be different from most of the math that we do today. It's just the concept is different. So let's go ahead and do this one. Find the area between the curve and the y-axis. So first of all, how do you know that we're integrating with respect to y here? What's the clue? Okay, there's one clue, right? The functions with respect to y. What's another reason why you know that? Yep, they're asking us to go to the y-axis instead of the x-axis. So those are your two indicators that we are integrating with respect to y, right? And I'm integrating the function f of y from what to what? 2 to 6. So that's it. There's your setup. After that, we're going to use our calculators. Now here's the thing. Our calculators don't do functions with respect to y. But that doesn't matter. We're just going to call it x anyway. The graph will not look like that. Okay? The graph will look the same, but on the x-axis instead, it'll look reflected. But it doesn't matter because you'll get the same area anyway. So go ahead and just type it in and see what you guys get, and we'll move on. So we're getting 10.667. Okay. All right. So there's a little secret here, and just do your best. Go ahead and solve it the way that you think. It's a student practice, but there's a little twist here. And if you can find it, awesome. If not, it's an easy fix, and I'll help you get it at the end. But for now, go ahead and see if you guys can solve it. So here's our setup, and we get 0. Now, why does it make 0? Why does that even make sense? Why could you just look at that and be like, oh, it's 0 from the beginning? You have one piece over here, and one piece here. One's positive, one's negative. Now, which piece is positive? That's right. A lot of people might want to say the one up here is the positive one, right? Because we're so used to thinking above is positive. But remember, we're integrating with respect to y. So now, actually, the one on the right side is the positive area. The one over here is negative. They're exactly the same shape, so they just cancel each other out. Okay? But I think in the past I've used my words loosely, and I haven't been really saying things correctly. So I'm going to try to say this correctly today. If you're ever asked for area, they don't want negative stuff. Okay? If you just saw a question like this with no picture and they just said evaluate the integral, then the answer would be 0, and that's good. But if they give you a picture like this and say find the area between the curves, They don't want you to think of that as negative. They want the actual area. So what should I do to get the actual area then? Absolute value. So did anybody do that? Oh, nice job. Now somebody in my 5th period noticed that. And the reason why you guys don't need to feel bad for noticing is because I've even called the negative area in the past. I shouldn't do that because that's not correct. Area is always positive. So I don't know what to call it though. So I call it negative area. But anyway, so what we're going to do is we're going to redo this with some absolute value bars actually because they want the area. And what did you get, Heather, when you did it? 0.5 is correct. All right. So maybe make a little note to yourself. Since we want area, it's all positive. But I like this problem though because it gives a chance to talk about how the fact that anything to the right is positive and anything to the left is negative. Now somebody in my 5th period noticed that as well. What made you guys want to do the absolute value bars? What made that click for you? Just habit from yesterday, or? Okay. Okay. Cool. That's a good answer. The way some of my 5th period put it was, remember how I said anytime it crosses more than twice? And so we're not really looking at 2 functions crossing, but since we're looking at where it goes through the y-axis, it is hitting that y-axis at more than 2 points, so that would be another good indicator. So anyway, so just know anytime they want absolute value, just know they always want the positive. I'm sorry, anytime they ask for area, they always want positive. So a little bit of a opportunity for me to pick up a mess I started there. So just know in the future, if they ever ask for area, it's positive. All right, so remember this as well? The one that's on top comes first, right? If you're finding area between curves. So how about when you're going horizontally and you want to find the area between 2 functions horizontally? Which one would come first? The one on the right. Because when you're looking at the x-axis, numbers that are to the right are greater than numbers to the left, right? So in this case, if f of y is to the right of g of y, then when you set up your integral to find the area between these 2 curves from D to C, the fy comes first and then the gy. Okay? So now that's pretty nasty looking, isn't it? You're actually going to find it's not that bad. So let's go ahead and do an example here. All right, so the first thing I'm going to ask you guys to do is I'm going to ask some bold soul to come up here and trace one of the functions. There's 2 functions on this graph, but I want somebody to trace one of them, just so we can kind of see them apart. Thank you, Jake. Oh, yeah, no, you will.
It's already chosen and you have to.
There's 2 functions up there. I just want you to trace one of them.
Alright, so.
So unless you actually want to use highlighters, you can just do this mentally in the future, but you have to be able to see them. So we have, thank you, Jacob, that is correct. We have 2 functions. We have one that's kind of like that Z shape there, and then we have that sideways parabola, right? You see them now? And we're finding the area between them, correct? All right. Now, Jacob did a little bit more than I asked for. He even color-coded which one he highlighted. How did he know that that was the one? It's a cubic, and hopefully we know that cubics have that double bending shape, right? So that's helpful to know as well. All right, so there it is. I feel like the other one should be highlighted too, just because it doesn't seem fair. So I'm gonna highlight the parabola now. There we go. All right. Now, I'm going to integrate this. from, now I'm going to do this two ways. I'm going to do this, I'm going to set it up as though I were doing it by hand without a calculator, because there's some value in that. Matter of fact, tomorrow we are going to do problems without calculators, but also I just think there's some value in doing it anyway. But then we're going to actually set it up for a calculator and use our calculators, okay? So if you're doing it by hand, you don't do absolute values. You actually have to make different integrals for where they cross, right? So from here to here, from this crossing point to this crossing point is going to be one integral. Now remember, I'm going with respect to y. So my limits have to be y values. So what are the y values from here to here? To 0. Good. Now for that particular portion right here, I'm looking for that shaded area. Which function is furthest to the right? The pink one, right? See how pink is to the right of the green? So since the pink is to the right of the green, it's going to be the negative y squared first, and then the green one second. Now I'm running out of space. I would like to write the rest of my equation over here, but I'm out of space. So I'm going to write it underneath with a plus. Okay, but you guys can write it to the right. Because now we're going to do the next part of this. So my next piece goes from what to what? 0 to 3, right? We're going from 0 up to this point. So that's from 0 up to 3. And in that case, which function is coming first? The green one. So that's negative y cubed plus 6y minus a negative y squared dy. And that would give me the area between those two curves horizontally with respect to y. Okay? But on a calculator, we don't really need to break this up, right? We can do it all at once. If I'm going to use a calculator, all right, we could do it all at once. We can go from what to what? From -2 all the way down here at the bottom, all the way up here to the top at 3. And it doesn't really matter which one you put first, so long as you do what? Put your absolute value bars on there. And that's what we're actually going to type into the calculator. But I do want you guys to know how to set it up as though you were doing it by hand. Okay, so go ahead and type that in. That's for no calculator, and that's for calculator. $10.417. Oh, I forgot my absolute value bars.
Oh, dude.
Stomp. Stoip. Joe! I gotta type it all again. Does anybody got it yet?
Yeah.
Okay, what'd you get? 21.08. Okay. All right, 21.08. Anything after the 8? Cool. There we go. So, now a question that was asked, and it's a good question, in my 5th period was, are you always going to give us the picture? Well, if I give you a graph and calculator, I shouldn't have to, right? because you can make the picture. The only difference is the picture won't really look like what it's supposed to, because it's only going to make it, it's going to look flipped as though it was with respect to x, right? But your intersection points and your area will all be exactly the same. You're just changing the orientation of the picture. I do actually plan on giving you the pictures, so just so you know. There's something about these where it's just kind of nice to be able to see it. All right, so here's one for you. I would like you to do 3 things. I would like you to give me the setup as though you were doing it by hand, the 2 separate integrals. And I would also like you to give me the setup as though you were doing it with a calculator. And then finally, the answer. And to save you guys a lot of writing, I mean, if you want to just call this first one here g of y, and we'll call this second one over here f of y. That way you don't got to keep writing long equations out over and over again. You can do that. Okay, so Heather, what's our first piece going to be going from what limits? 0 to 2. That would be our second one. Okay, good. So our first piece from here to here, the y values are -3 to 0, and then from after that it's from 0 to 2. So John, on the first interval from -3 to 0, which one comes first, G or F? G minus F dy. Now why? Because we have 2 functions here. One of them is a linear function, and that's this guy. So F is the straight line, G is the bending one. And as you can see on that interval, G is further to the right than the straight line. All right, so let's go ahead and take a look at the next piece there, Joanna. The second piece will be what minus what then? Good. And that's if we were doing it by hand. Now, if we're doing it on a calculator, we don't have to set it up as 2 separate intervals. Kirsten, if I wanted to do it on a calculator, I just need to go from what to what? That's correct. And the order, whether you do F minus G or G minus F, doesn't matter, so I'll just put one of those in there. And then we get it typed into our calculator and figure it out. And quickly, did you get to calculate it yet? Okay. Jackie, did you get to calculate it yet? What did you get? 10.542. All right, there you guys go. So that's that. So we've looked at integration. We're doing integration with respect to y, right? In this case, we're looking area between curves. The big takeaway there is which one's on the right, which one's on the left. That's your setup there. And also your limits are, once again, y values instead of x values. You're integrated from top to bottom. So last thing that we'll look at is implicit functions, functions that are neither solved for x or y. And we're going to look specifically at circles and ellipses. Those are some common questions that you can expect to see. So I don't think I printed this one for you. So I'm going to wait a second for you guys to go ahead and copy that. I'm going to change the instructions though. I'm going to put find the area of the ellipse. This is actually the equation of an ellipse. So, let's do a little pre-cal review for a moment here. Okay. You could probably get away without doing a lot of the stuff I'm going to do up front to just get the answer. But a lot of the stuff I'm going to do up front is to help you understand why the part we're doing makes sense. So the first thing I want you guys to do, remember, is how to graph one of these things. Not too bad, actually. First of all, you might want to write this stuff with me. I don't think I got to this in my pre-calculus students, and I don't know if my pre-calculus students from last year did this in Algebra 2 or not. It's hit or miss for a lot of students. but this is an ellipse. Now, if you had Mr. McMillan, maybe you guys covered these. But this is what we call an ellipse. An ellipse is like an oval. It's like a stretched out circle, okay? And it has a center, okay? Just like a circle has a center to it. The center of the ellipse is H and K. Notice that it's the opposite signs too, like this is minus H and minus K, but these are positives. It'll be minus. It'll be opposite sign, I mean. The A and the B tell you the horizontal stretch and the vertical stretch. As far as I know, they don't have any official words for these, so I'm kind of making this up when I say horizontal stretch and vertical stretch, but distance from the middle is what I mean by that. So what I'm going to do is I'm going to use these facts now to graph this shape over here, okay? So first of all, my center is the H and the K, the number you subtract from the X and the Y. So in this case, what is my center? It was what? There you go, 4, 0. We have a 4 here, opposite sign, right? And there's nothing there, so it's 0. So that's my center. So I'm going to put a dot at 4, 0, and that's going to be the center of my ellipse. Okay. Now the next thing is I need to find out what A is. A is this number down here, but it's being squared. So if this is A squared, then what does A equal? Huh? 4. That's going to be my horizontal stretch. In other words, the sides of my ellipse are going to be 4 spaces away from the center on both sides. So from here I'm going to go over 4. That's as far as my ellipse goes to the right. And then I'm going to go left 4 as well. That's as far as it goes to the left. The B gives me my vertical stretch. So this is, once again, this is B squared. So that means that B is 2. So we're going to stretch 2 up and 2 down from the center. So how about it? Does this look familiar to anybody in here? Yeah? Did you do it with McMillan? In Algebra 2 or Pre-Cal? Oh, so it's hard to tell. There's your ellipse. So I'm being asked basically to find the area inside of that shape. So what the heck has this got to do with our lesson today? I shall show you. Can I erase all this good stuff except for the graph? So that's how you graph them. But there's more. Now, we want to do integration. And to do integration, we can either integrate with respect to x vertically, right? Or, oops, too far. Or I can integrate with respect to y and go this way. Either way, you're going to get the answer, right? So you can integrate with respect to y or with respect to x. So let me ask you this. In order to do that, we need to get one of these variables by itself, either the x or the y. Which one looks like it'd be easier to get by itself? That's the one you want to get by itself. It doesn't really matter. You could do both, either one, but go with the one that's easier. So I would start by taking this whole chunk here and subtracting it to the other side. So I would get this. And then I would multiply everything by 4 to get rid of that denominator under the y there. So if I multiply this by 4, I get y squared. This by 4, I get 4. This by 4, I get and then luckily these reduce nicely. 4 goes into 16 4 times, right? What's the last step I need to do? The square root. And here's where something that's people forget to do, but it's actually very important in this problem. Plus and minus. And I'll explain why that's important while I wait for you guys to finish writing. But all I've done so far is I've gotten the y by itself. Okay, so why is it important you have the plus and the minus? Well, do you guys remember the vertical line test? Does this sound familiar at least? Okay, the vertical line test is a rule that says that something is a function if, when you draw a vertical line, it only hits the curve once. So is this a function? No, it's not. But we're trying to make it a function, right? I'm trying to make this a function that is of some kind instead of some crazy implicit equation, right? I just want it to be a function so I can integrate it like I do all my other ones. The problem is it's not. But what we actually did here is we ended up with two functions, okay? We have a positive square root of all that good stuff and a negative. Now remember back when we did circles, the positive part is the what? That's smart, but no, it's the top. So positive is the top. Remember when we did circles? Okay, so the positive part is the top, and the negative part is the bottom. Now, if I think of those as two separate functions, are both of them functions? Yeah, because then the vertical line hits each one of them once, right? So that's kind of the cool thing there, is it breaks it up into two pieces for you. Now, why is that also helpful to us? Because now we're looking at the area between two functions, right? So we took an ellipse, we rewrote it so it's really two functions, and to find the area inside of it is really just finding the area between two functions. All right. Now here's another question for you. I solved for y. So is this a function of x or of y? In other words, am I going to integrate with respect to x or with respect to y? With respect to x. When you have the y by itself, whenever your equation has x's inside, that's a dx problem. Whenever you have y's inside, that's a dy problem. Now I'm going to come back to what you said. You said left and right. Okay. If we had solved for x instead, then we would have gotten a different looking equation, and it would have still had a plus and a minus. But the plus would be the side that is actually to the right, and the minus would be the side that's to the left. So I'm glad you brought that up, because if it turned out to be a function with respect to y, it would be left and right instead of top and bottom. But anyway, let's go ahead and actually do the problem now. So we've already decided that I am integrating with respect to what? X, which means that my limits are going to be x values. So I'm integrating from what to what? Huh? Yes, 8 is the answer. So we're going from this place where they touch to this place where they touch, right? 0 to 8. And it's got to be top minus bottom. So which one is the top one? So 4 minus... Oh, I wrote it wrong here. This was supposed to be a 4. Sorry about that. So that's the top minus the bottom. And the bottom is the same thing but negative, right? Sorry, I'm running out of space there. What do double negatives become? At this point, you really could just type it in the calculator the way I've got it written, but I'm going to simplify it and show you something kind of interesting. But you could just plug it in at this point, right? So since we're subtracting a negative, it becomes this, which means I've really just got the same thing being added to itself, right? So really what I can do is write it once and double it, right? Save you a little bit of writing and typing maybe. This is what I would want to type into my calculator. But like I said, you could do it up here. All right, so now in the future, how can we do this without doing all that crazy hard work, you know? Well, basically just solve for a variable, right? You don't even need to see the graph for that, right? Put that here with a 2 in the front. The only place you're going to have trouble is figuring out what your limits are. Without the picture, it's kind of hard to tell what your limits are. So maybe you could do it mentally, I don't know. But really, you don't need to do all the other extra work that I was doing there. So like you could skip all this, and if you can do it mentally, you could skip the picture. So really you just need to get a variable by itself and put a 2 in the front. Just got to be able to find those limits. But there it is. There it is. All right, so can I erase? I'm not going to find the answer if you don't mind. I'm just going to skip the calculator part. Do you want to do it? Okay. Let us know what you get. I'll check it while you're working and let you know if you're right. We only have 5 minutes. Can you do it? 5 minutes. So here's the graph, and here's what we get if we get the x by itself. Now, since we've got x by itself, the positive portion is going to be the portion of the graph that is to the right, and the negative portion is going to be the portion that is to the left. And we're looking to find the area between these two curves horizontally. So that means we're doing with respect to y. Now, I'm just going to use the shortcut that we saw in the last one. You really only need to put the radical one time and put a 2 in the front, because both halves are symmetrical there, so they're exactly the same. And you get that, and then you punch in your answer there to the calculator, and you end up getting something like 9.425. Okay, and there you have it. See you next time.